Hi, this is Professor Fernandez, and we're talking here about Module 3 in Lesson 2. We're going to talk about the dot product in this module. So this is in the first video in this lesson, one of the ways I mentioned that we can, quote, multiply vectors. So let's get a little insight into motivation for this concept. In the previous video, in Module 2, we talked about the definition of vector addition and scalar multiplication. So let me start there, right? Let's start with a vector u with components u1, u2, u3, and let's use some of those properties, right? We can decompose this, we're using the properties now sort of in reverse order, into the following sum of vectors. So if I go back to my, and I'll scroll up here, I still have all the scribbles from the previous video. If I go back to this definition, I'm kind of using this property of vector addition in reverse. I'm saying that I can take these, if I scroll back down, take this, for example, these two vectors, and if I add them, I would end up adding their components. And then if I take this vector and that one, if I add them, I would end up adding their components, getting me back to the vector I started with. So I'm using the definition that we talked about in the previous video as a way to decompose a vector into simpler vectors and sums of simpler vectors. And then I'm going to do the same thing with the scalar portion of that definition, the third part. I'm going to pull out this u1 and express this sum in terms of a sum of three very special vectors, which we are very shortly going to give those names. Great. So again, as a check, by my definitions that we talked about in the previous video, to calculate this vector, I would multiply u1 into all of the components, obtaining that vector. So these are in fact the same equations, just the same expressions, just with the u1, u2, u3 outside the vector. So at this point, we have been able to decompose any vector u in R3, and you can see, of course, we can do this the same way in R2 or in any dimensions, as a sum of multiples of very specific vectors and very simple vectors. So these three vectors are what are called the standard unit vectors. And this is the definition down here that I'll get to in a minute. But we call this first vector I hat, the second vector j hat, and the third vector k hat. You might, from the previous videos, recognize that the hat means that these vectors are unit vectors, and they are indeed, right? They have components all 0 except for 1 somewhere. So when I add the squares of these components, I always get 1. Then I take the square root, I get 1 again. So it's a length 1 vector, it's a unit vector. And then I refers to the fact that the x component is 1. J refers to the fact that the y component is 1. And then k refers to the fact that the z component is 1. And all of the components in these vectors are 0. Great, so these are the standard unit vectors. And so that leads us to our definition, just to formalize that. So the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 are the standard unit vectors of R3. We could have played a similar game, and I'll just write this out very quickly, with the unit vectors, with a vector in R2. So we could decompose this as follows. And this would then be u1 I hat plus u2 j hat. Okay, so similar decomposition to what we just did with a vector in R3. Okay, so what we've just shown shows us that we can re-express any vector in R3 or R2 in terms of a sum of multiples of unit vectors. And that should make sense in a way, and I'll explain that very visually in a minute, but let me focus on the unit vectors themselves. So let's talk about those unit vectors. So if I go to R3 now, and I try to plot my unit vectors, let's see what they look like. Well, I have I hat, which is the vector that just goes 1 unit in the x direction. So that's I hat. And then I have j hat, which is the vector that just goes 1 unit in the y direction, j hat. And then I have z hat, the vector that goes 1 unit, k hat, the one vector that goes 1 unit in the z direction. So I have this this nice trio of vectors that do exactly all of the work, if you will, of moving us around R3. What do I mean by that? What I mean by that is up here. Any vector in R3 can be written as a sum of multiples of those 3 vectors. So later on, this becomes a notion of a basis in linear algebra if you get there, but we won't need that. Suffice it to say that this property makes these 3 vectors very special. The fact that you can get anywhere in R3 by moving along the x-axis and then moving along the y-axis and then moving along the k-axis. Remember, vectors have a direction associated with them. So I hat literally points in the direction of the x-axis, but it has length 1, so that's useful because you can use that to travel 7 units along the x-axis. That would be 7 I hat. J hat similarly has points literally in the direction of the y-axis, and k hat literally in the direction of the z-axis. So that's visually one of the nice things about unit vectors, and algebraically also, that it enables us to then move around in R3 by just going certain amounts in the x direction, certain amount in the y, certain amount in the z direction along I, j, and k hats. Great. So another thing that we notice about these 3 vectors is that they're orthogonal. So that's also interesting. So I and k are orthogonal, j and k are orthogonal, and I and j are orthogonal. And that begs the question, how do we capture this orthogonality mathematically? I've captured it here in a picture by drawing the familiar notion of a right angle between these 3 lines, segments, and vectors. But how do we capture that mathematically in an equation or in some concept? So that leads next to the notion of the dot product. So I'll go through the definition of the dot product first, and then we'll get back to the unit vectors to see how it captures this orthogonality. So this is on page 588 of the Apex Calculus book. It says, suppose I have 2 vectors u and v in R3. The dot product of these 2 vectors, the new notation here is u dot v, so that's this notation up here. The dot product u dot v is defined as the number this. So first of all, the dot product is a number. So that's very important to remember. In a future video, we'll talk about the cross product, a different way to, quote, multiply vectors. The cross product will yield a vector. So it's very easy to get those 2 confused. The dot product yields a number. And what is that number? How is it defined? Well, the dot product is this. And what is this? This is the sum of products of the respective components of u and v. So we'll do some examples in a minute, but let me just very quickly relate this back to I hat and j hat. So that'll be a quick example. So what if we want to calculate I hat dot j hat? Well, I hat is the vector along the x direction, unit vector, and then j hat is the unit vector along the y direction. So what do I do here? I multiply the x components plus multiply the y components plus multiply the z components. 0 times 0. And I get 0 plus 0 plus 0, I get 0. So I hat dot j hat equals 0. And, of course, anytime you get 0 in math, you might suspect that there's something special going on, or that you made a bunch of mistakes somewhere. Often both of them are equally likely. In this case, though, there is something special going on. So we already saw up here that I hat, j hat, and k hat are all mutually perpendicular to each other, or orthogonal. That's another word to say this. And here we are calculating the dot product and getting 0. So, if we calculated the dot product of j hat with k, we would also get 0. if we calculated the dot product of I hat with k, we would also get 0. So, perhaps getting 0 for the dot product has something to do with orthogonality, is what I'm trying to convince you of. And that is indeed what happens, what turns out to be the case. So here is the theorem that is going to connect those concepts for us. So this is the dot product in angles, page 590 in the book. So suppose that I have two vectors, u and v, and let theta between 0 and pi be the angle between u and v. So let me just stop there. Here is u. Here is v. You might ask me, what is theta? How do I conceive of the angle between u and v? Okay, well, one thing you can do is that you can bring these two together so that you can look at the angle between u and v. So if I bring this over here, remember, it's still the same vector based on an earlier definition that we introduced, that if you just translate, you don't rotate or lengthen or shorten the vector, it's the same vector. Now we can talk about the angle theta. Okay, and it doesn't matter if we're talking about the angle between u and v or the angle between v and u, it's the same angle. It doesn't matter how you refer to it. Okay, so now we're going to then see in this theorem, the conclusion is that the dot product is the product of the two lengths of the vectors times the cosine of the angle between them. So there is what we sort of started to suspect based on all of this work up here, that somehow the dot product relates to the angle between the two vectors. And there it is in the equation. There are various ways to prove this theorem. So this link, if you follow it, you will see a proof of this theorem in R2. It's a little easier to visualize than a proof in R3. But if you are adept enough with the vector arithmetic that we just talked about in the previous video, and some additional properties of the dot product, which you'll find on page 589 of the textbook, then you will be able to do this proof without needing to visualize anything. So properties of dot product. So I encourage you to check out that part of the textbook to see what those properties are. Many of them are familiar properties, like the dot product of u with a sum of two vectors is the sum of the dot products, things like that. Okay, great. So one last little bit then to connect everything, and then we'll do an example. Definition, the orthogonality of vectors. So we say that two non-zero vectors, I'll mention why in a bit, u and v are orthogonal or perpendicular when the dot product is 0. So that closes the loop, if you will, from where we started. Thinking about I hat, j hat, k hat being mutually perpendicular, mutually orthogonal. And then thinking that it has something to do with the dot product once we calculate those. So indeed, from here on out, if you take the dot product of two vectors and you get 0, we will then say that those two vectors are mutually perpendicular. And you can see where this comes from, right? We'll just go back to this theorem. If u dot v is 0, and knowing that this is equal to this expression, then as long as the vectors are non-zero, this is part of the reason that it's assumed here, right? Then the lengths are non-zero. Goes back to a property we talked about in a previous video. So we can divide by this length, both sides of the equation. And we get cosine of theta equals 0. And because we have defined the dot product to be such that the angle theta is between 0 and pi, I'll mention why that is in a minute, we start searching for values of theta which could give us 0 in that range, in that domain, and the only one that works is theta equals pi. Oops, sorry, theta equals pi over 2. So pi over 2, which is 90 degrees. So cosine of 90 degrees is 0. Cosine of 0 is 1. Cosine of 180 degrees, which is pi, is negative 1. So that is the perpendicular outcome. So that's 90 degrees. That's orthogonal. Great. So let me just close that loop earlier that I mentioned as to why we restrict theta to be between 0 and pi. Let's think just very quickly. If I drew two vectors here, here's u, here's v, here's the angle between them. So right now it's an acute angle, so it's less than 90 degrees. What if I look at, make theta bigger? So here it is at 90 degrees. Here's u, here's v. What if I make it obtuse? So here it is bigger than 9 degrees. Right? And then what if I get to the point where it is exactly 180 degrees? So here's u and here's v. If I keep going and I try to make it bigger than 180 degrees, then, well, theta is supposed to be the angle between the two vectors. This would not be what I would call an angle between the two vectors, right? So that doesn't make a lot of sense. This is what I would call the angle between the two vectors. So this kind of explains why we take theta to be between 0 and pi. Once you get to pi, if you keep going with the original conception of your angle, it's no longer the angle between the two vectors. It's the angle like from the outside of one to the other. Some strange way of thinking about it. So that explains the range here for theta from 0 to pi. Okay, so we have done a lot here. So let's do an example to illustrate how to bring all this together. So consider these three vectors u, v, and w. First of all, we are going to express u in terms of the standard unit vectors and then identify the x and y components. So let's do that. So u is 3, 1. Using the same manipulations we did before, this is 3 times 1, 0, plus 1 times 0, 1. And that's 3 I hats plus 1 j hats. Okay. And then identify the x and y components. The reason I put that in there is to foreshadow what is going to happen later that I'll write down after this example, but also in the practice problems. You'll notice that the numbers that go here, and let me just write out the 1. You'll notice that the numbers that go here are the same numbers as the components of the vector u. And that's not a coincidence, and that's kind of the point of this example, that the components of the vector, the x and y components, are the x and y components of the standard unit vector representation. So this 3 goes in front of the I hat because this is the x component. This 1 goes in front of the j hat because it's the y component. And that's one thing that we learned from this example. Okay, number 2, find the angle between the vectors u and w. So u dot w equals, well, so let me just say that I defaulted to calculating the dot product. Why? Because if you scroll up, that is, as of now, the only way that we have to connect the angle between the vectors to the dot product, which is something that I can calculate from the two vectors. So I'm going to calculate u dot w here, 3, 1 dot 1, 1, and that's product of the x components plus product of the y components. That's 4. And then also I need to calculate the norm of u and the norm of w. So that is the sum of the squares of the components. Square root of 9 plus 1, square root of 10. And then over here, square root of 1 squared plus 1 squared, that's square root of 2. So therefore, the cosine of theta is the dot products divided by these norms. That was our theorem earlier. So I get 4 divided by square root of 10 times square root of 2. And then we can do all sorts of simplifications here. So let's see. Square root of 10 is square root of 2 times square root of 5. And this is another square root of 2. So that gives us a 2 here, square root of 5. So that gives us a 2 over square root of 5. Okay, so we can calculate theta as the arc cosine, inverse cosine of 2 over square root of 5. I don't have a calculator with me, so I can't tell you what this approximates to. You can certainly pull out a calculator or go to Wolfram Alpha or somewhere and figure that out. But this is the exact value. When you calculate this, you will be approximating it. So in a sense, this is the better answer. So we have found the angle between the two vectors, even though we can't pin it down as a numerical approximation. So we could do that certainly if we wanted to. So number 3 says, are the vectors u and v orthogonal? So that's a question that we can't answer without knowing the exact value of theta, because we know that theta is not pi over 2. How do we know that? Well, cosine of pi over 2 would be equal to 1. And cosine of theta is, in this case, 2 over square root of 5, which is definitely not 1. So the answer is no. Theta is not equal to pi over 2. Okay, so these vectors are not orthogonal. And then number 4, show that u dot I hat equals 3 and u dot j hat equals 1. Okay, so again, this is meant to foreshadow what I will do in a minute to connect the x and y components to u hat and j hat. So I'm going to do u 3, 1, 3, 1 dot I hat 1, 0. So I multiply the x components together and I add the product of the y components, which is 0, so I just get 3. And then u dot j hat 3, 1 dot 0, 1. Similar thing, so here I get 3 times 0 plus 1 times 1, so I get just 1. So that's basically all that I asked you to show for number 4, that in fact u dot I is 3 and u dot j is 1. But again, this ends the example, so now I'm going to launch into basically why I asked you to show this. and I'm going to give myself a bit more space down here to just explain why. So this fourth part of the example is meant to be a teaser introduction to the fact that a vector u in R3 can be written in this form. So I will write this down. And actually, let's just talk about it for R2 so that we save a little bit of time. And what am I talking about here? So I'm talking about the fact that, as we said earlier, the number in front of I hat is the x component, and the number in front of j hat is the y component. We also said earlier that the dot product produces a number. So you put these things together, and this claim is that the x component of any vector is equal to the dot product of the vector with I hat. The y component of any vector is equal to the dot product of the vector with j hat. And that's exactly what this example was meant to, start to convince you of. This particular decomposition of the vector is very useful, and we won't necessarily use it in the rest of the course. It is useful for lots of applications and useful later on in future courses like linear algebra, for talking about orthogonality and multiple dimensions. But you will explore this decomposition in the practice problems if you're interested in this view of it. Suffice it to say that this way of writing a vector u in 2 dimensions, and we could, if we just added a third component here, this would be the 3-dimensional extension of this idea. This idea is neat because it brings together pretty much everything we've been talking about so far in this lesson. The notion of vectors, the notion of length, unit vectors, the notion of vector arithmetic, adding them, and now the new notion of dot products, and certainly the notion of components of a vector. So all of that is in here. So if this representation of u makes a lot of sense, then I think we're on a good track. This is all new stuff, so it might take a while for it to make sense anyway. Hence, the suggestion to work on the practice problems. I don't normally preview the practice problems, but because of the tie-in with this, I do want to talk about one thing. The dot product, because it's related to angles between vectors, is also related to something called projection. So if I wanted to, for example, down here, look at this vector u, and I want to project it along the vector v, by which I mean, what if I were standing right on top of you and I had a flashlight and I turned it on? The shadow that this light would cast, right, where would it stop? I could call that length the projection of u onto v. And that is a concept which has interesting applications in all sorts of fields and later on in the course as well. So I do encourage you to go ahead and work through some of these practice problems, and you will learn about the orthogonal projection. This is also in the textbook if you just want to read about it and not necessarily work through the practice problems. And then, of course, as I mentioned in an earlier video, many of the practice problems that I suggest have real-world applications associated with them. Here's a really nice one where you can look at, find what's called the bond angle of the methane molecule, CH4. So this is really cool. So here's a methane molecule, and if you construct vectors connecting the carbon atom to the hydrogen atoms, and then you ask what is the angle between this two consecutive hydrogen atoms and the central carbon atom, you can calculate this using dot products. So that's pretty cool. This is something that you might have just been told about in a chemistry course, or maybe even told how to calculate, but now using what we just learned about, you can actually do it yourself. And it's very nice application. Great, so the star of this show is pretty much on this, all on this page. The definition of the dot product, to recap, dot product is the sum of products of components, respectively, of respective components of U and V. It is a number, and the dot product is related to the angle between two vectors, between the angles between 0 and pi, by this formula. And then as long as we're talking about non-zero vectors, then if their dot product is 0, we call those two vectors orthogonal. So we now have a way to not only in this lesson visualize vectors, add, subtract vectors, we have a way to talk about the angle between two vectors and a way to decompose vectors into these standard unit vectors I hat, j hat, and k hat. Great, so I'll see you in the next video.